All right, so logarithmic functions. Let's jump right into the formulas, and then as we go, I want to give you a little bit of a reminder of what logarithms even are, just in case. I know I did this a little bit in the last video, but just in case you've forgotten, because if we speak truly, we don't use logarithms often in really algebra or pre-algebra or pre-calculus, calculus. We don't use them often. We do eventually, like the higher up you get, the more useful, especially functions like e to the x turn out to be. But up until this point, we haven't had tons and tons of practice with them. So I'm going to talk about them knowing that you understand the basics, but assuming that we might have forgotten some of the key pieces. So that being said, let's look at our two formula examples here. We're talking about logarithms that have a base of just any type of constant, kind of like you see the correspondence between this and the exponential equations, obviously. So a base where it's just a number. So here in red, we see that the base is a. That could be 2, it could be 10, it could be 5, whatever. But for the second equation, we look at natural log, and remember that natural log is a base of e, the Euler number. Now, one other important thing to remember is if you ever see a logarithm just written out like this, like, I don't know, log of x, with no base listed, remember that that base is 10. So if none is included, we assume a base of 10. All right, now that we have those basics covered. Whoops. All right. So the derivative rule, if we're taking the derivative with respect to x of a logarithm base a of u, which again represents just some function with respect to x, the formula is 1 over that function u times the natural log of a, the base, times the derivative of the inside function, du dx. And that is that. You probably see there's a little bit, it's reminiscent of what we saw in the exponential formulas as well. So there is obviously that connection because logarithms and exponential functions are inverse operations of each other. Okay, what happens if we have natural log where we have a base of e? Well, what would happen is we use the same formula. We would have 1 over the function u, but we would have natural log of e times the derivative of the inside function. And just like in the topic 1 video, we remember that natural log of e is really log base e of e. That is just 1. So that goes away. It's u times 1. And so that shows us that the derivative with respect to x of just the natural log of some function u is just 1 over u du dx. And this is kind of an interesting connection because 1 over u is, let's say, actually, let me take a moment over here to write, let's say it was natural log of x. Okay, so we're assuming y equals natural log of x, and we want to find y prime. Using this formula, we would find that the derivative is 1 over x times dx, or just times 1. So the derivative of natural log of x is 1 over x. Now 1 over x is really just x to the negative 1, right? That's another way of saying that. So we see that there's actually a connection between derivatives of natural log and power functions with a negative exponent. So actually not a power function, but like a, well, it would fall into the same rule, right? If we were to find y prime, I guess is what I mean. It's like a power function with a negative power, which is really a rational function. So then the derivative of x to the negative 1 would be negative 1x to the negative 2, which is the same as negative 1 over x squared. So we actually see this link between a natural log function and these rational negative power functions that you kind of wouldn't expect to see. It's kind of like, it sometimes throws people off when they start to take the derivative, like, wait, I was dealing with a logarithm, which makes me think of like e to the x, and now I'm dealing with x to the negative 1. How did that happen? Well, there is a relationship there. Anyway, back to these rules. we have, just like the last one, just two that we need to remember. And the most important one really is this one here. That's the one we're going to use the most often. All right, let's use this in practice. Let's apply it to a problem. Now remember something about logarithms. Let's go back to this. I'm going to erase this here. Remember this relationship between exponential functions and logarithms. So if I had an exponential function y equals a to the x, I can rewrite that using a logarithm in this way. We would say log base a, because the base, this is called the base of the exponential or the base of the exponent, and this is also called the base of the logarithm. So rewriting this function into logarithmic form, the a and the a, base and base, of some function, so in this case y represents the whole like some function thing, equals an exponent. So one phrase that I always use in my classes is that a logarithm always outputs an exponent. So if you think about a logarithm as a little mathematical machine, it always spits out an exponent. So you can write that down if you want. And a logarithm always outputs an exponent. Or another way of saying it is, a logarithm actually is an exponent, right? Because we can make it as an equivalent to the exponent itself. So a logarithm basically is an exponent. And so we're rewriting these, the top equation and the bottom equation are the same expression, the same mathematical, it's describing the same mathematical situation, but using different terminology. That's really, really important even in calculus. And here's why. Take a look at this example up here. We have y equals x to the x, which is kind of an interesting situation. It doesn't really fit with any of our formulas because we're going to look for y prime, or trying to figure out what that is. But I don't have a formula that allows us to derive a variable taken to another variable. We have e to the u, we have a to the u. In both of those cases, the base is a constant, it's just a number. But here we see that the base and the exponent are both variables. And so we need to use logarithms to rearrange this equation. Now, if you remember from pre-calculus or algebra 2, we learned that we can use logarithms to simplify an exponent. So, for instance, I could take the logarithm of each side of this equation, natural log of y, and I could take the natural log of x to the x. And that's just, of course, because if I use a mathematical operation on the left side of an equation, we can do it on the right as well. That's not so much the fancy important part. The important part about logarithms is, remember, a logarithm is an exponent. So I can rewrite, right here I have natural log of y is basically an exponent. Natural log of x to the x basically is an exponent. So I can write this exponent either up here, or I can move it to the front, and it would be true either way, right? Because a logarithm, including a natural logarithm, is an exponent. So whether I write the exponent in the little position up at the top right corner, or if I list it out front with the logarithm, either place is allowed. And that's a rule that you should have learned last year and the year before. If you need me to refresh you on that in class, we can absolutely go over that. But that's super important. When we're dealing with logarithms, one of the reasons they're so useful is because it allows us to take an exponent that is stuck up in the, or a variable that's stuck up in an exponent, and move it to where we can actually do some math. That's really, because you can't really do much math when it's stuck up there, but we can do some math with it if we bring it down to the front. Okay, so let's do that. Let's rewrite it then as natural log of y equals x times the natural log of x. That's how we can rewrite it. Now, we couldn't derive it up here because it was in a form that didn't fit any of our formula, any of our exponential formulas, I should say. But now we have the situation where this is in a state that I could use these formulas to derive it, right? Because we have two natural log expressions. On the left side of our equation, we're just deriving natural log of y using what we know about implicit differentiation. So natural log of y is really like a chain rule. We would say the derivative of a natural log is 1 over u. So 1 over y times dy dx. So just your typical implicit differentiation problem. We're done deriving the left side. So we just transitioned from simplifying to we're actually moving down the ladder. Now we're going to try to derive it. And sorry, I feel like I should write this here, but I don't want to squish my problem too much. All right, so we're moving down the ladder. We derived the left side. Now let's look at the right side. This is really a product rule situation because we have u is x and v is natural log of x. That means that u prime is just 1, and that means that v prime is just 1 over x. We talked about that using our formula again, right? Just 1 over x. So using our equation, v u prime is just natural log of x times 1. So that's just natural log of x, plus u v prime. That would be x times 1 over x. Well, x times 1 over x is really just x over x, right? X over 1 times 1 over x. So that's just 1. X over x is just 1. Why don't we just write 1? Because that's a lot easier. You can write it as 2 steps in your notes if you want to make sure you don't forget that. But really, we're just using that formula, v u prime plus u v prime. And we get natural log of x plus 1. And we said the tricky thing about implicit differentiation is knowing when to stop. We can't really stop here because we know we have our answer when we have dy dx equals a bunch of stuff. And right now, the only thing keeping us from that is 1 over y. We need to move that. If we want to get rid of that 1 over y, we can multiply both sides by y, right? That would cancel it out. So multiply the left side by y, that cancels this. Multiply the right side by y, and we get a nice answer of the derivative of y with respect to x, or y prime, is just y times natural log x plus 1. And that is the answer. A reminder, here I'm going to do this let me erase this from before. So looking at this, we came down to an answer of, we started with y equals x to the x. And we discovered that the derivative, dy dx, is just y times, that looks like I wrote an h instead of ln, natural log of x plus 1. So that's what we did our deriving. We moved down the ladder from y to y prime. And that is the answer. If for some reason, and actually I borrowed this question from our textbook, and one of the things that they want you to do in this problem in particular is they want you to give your answer in terms of x only. And we know how to do that, right? We notice that, so dy dx on the left, that's fine, but we have a y still in our equation. And sometimes we don't want that because sometimes it kind of keeps our equation from looking complete. But we know what y equals. Y equals x to the x. And so if we're asked to give this answer only in terms of x, we can change that very easily by plugging in x to the x for y. So we would change this just by plugging it in by substitution, x to the x times the natural log of x plus 1. So don't get worried if they ask you to do that. It's a simple fix to change it from in terms of y to in terms of x. All right, so we covered a lot of information here. The most important, or I should say at least, well, the reason I'm going to say this is the most important is because it's the new stuff. The new stuff you just learned how to do is this, the two formulas circled in green. How to derive a logarithm with a base of a, whatever that is, and how to derive a logarithm that has a base of e, the Euler number, which is a natural logarithm. Both of those are important. The natural log formula gets used the most often. So that's the one you really, really want to remember. It's also the easier one, which is kind of nice. It's just 1 over u du dx. Then subsequent to that, we went back and we talked about what we know about logarithms in general. We remembered that a logarithm always outputs an exponent. So we can rewrite any exponential expression in a logarithmic form, and we can kind of keep the integrity of the function. We also talked about how logarithms can be used to simplify kind of weird equations like this, y equals x to the x. We can take the logarithm of both sides, which allows us to bring the exponent down, and we went through that whole process. That's not new information, but you might be feeling a little rusty on that, so make sure you have all that in your notes, and trust me, we will have time to practice that in class for sure. But that's all very important as well. And then lastly, we kind of reviewed the idea of implicit differentiation and how to make sure that we write our answer in the terms that we're asked to write it in. Sometimes it might be okay to have it in terms of x and y. Sometimes we may be asked to put our answers simply in terms of x, and then we want to make sure we substitute. All right, that is the end of this whole unit. So unit 2, you now have all the information. We still have to finish working through some example problems, but you can pat yourself on the back a little bit. Well done. It will be fun to wrap this part up and move into unit 3 in the next week or so. All right, good luck with that, and I will see you in class.